Welcome to lecture 1 of set theory. We will start with basic concepts of set theory and then we will move ahead slowly. Okay, so what do you understand by a set? Is set any collection of any random things? Well, partially true. Set is well-defined collection of objects. Now what does well-defined mean? Well-defined means something which is mathematically true or false. There can be no ambiguity. So remember, no ambiguity is allowed. Alright, fine. So some examples we'll see of set theory. The first one will be XYZ. What is XYZ? We can say alphabets occurring after W. Okay. Then is this a set? A2, is it a set? Well, yes, well-defined collection. You can say these are natural numbers less than 9. Yes, that is true. Okay. Then this A3. What is this? 0, 2, 4, 6, 8. Yeah, it is set of even numbers. Okay. Then A4. Is this a set? All the X such that X is a good cricketer. Do you think it is a set? Is it? So how do you define good cricketer? It is not a mathematical statement, right? You don't know who is good, who is bad. Somebody good for you may not be good for me. So we cannot define A4 as a set. Alright? Next. So we saw that examples A1, A2, A3 were set and A4 is not a set. Right? Okay. And we already saw why. Fine. Then what is cardinality of a set? Cardinality is number of elements in the set. That's it. Okay. So this is simple, right? Alright. Yeah. So can cardinality be 0? Can you have an empty set? Well, yes, there is a notion known as empty set. It means there is a set having no elements. So how can you define it? Something which is empty. How do you define something which is empty? Some condition which is never true, right? So something like all those X such that X is greater than 1 and less than 1. So you focus on this word, logical word and. So can you have any X which holds for both these relations? No. So you cannot have any such X and hence your A5 will be an empty set. Alright. A6. A6 is all those X such that X is not equal to X. So can you have any number or any object which is not equal to itself? That can never be true, right? So again A6 becomes empty because it cannot contain any X satisfying this relation. Okay. So when do you say when are two sets equal? Yeah, let us see that. So logically all the objects inside should be equal, right? Yeah, they should be same. Equal means they should be exactly same. Okay. Then let us see this A5. A7. A7 is 3, 6, 9, 12. And A8 is all those 3x such that x is a natural number and x is less than 5. So what does this set mean? If x is less than 5 it means, and it is a natural number, it means x is 1, 2, 3, 4. And your A8 is 3x. That means 3 into 1 which is 3, comma 3 into 2 which is 6, comma 3 into 3 which is 9, and finally 3 into 4 because your x should be less than 5. So you go only up to 4. So that makes 9, comma 12. So is it exactly equal to A7? Well, yes. So all the elements, since every element in A7 is equal to element in A8. So irrespective of the orders, you can say these two sets are equal. So what are the two conditions for them being equal? The number of elements should be same. So there should be, if there are 4 elements here, you should have only 4 elements here, which we saw already because of this condition. And all the elements should be equal to one another. Okay. So we saw A7 and A8 are equal. What about this set A9? A9 is all the 3x such that x belongs to a set of natural numbers and x is less than 10. So you can clearly see it is an extension of A8. So do you think all the elements of A8 are also elements of A9, or is it vice versa? Apparently, because this has less number of elements in it, all the elements of this should be in this because rest of the conditions are same, right? Yes. So then what do we say? In this case we say A7 or A8, because both of them are equal, is a subset of A9. That is, every element of A8 belongs to or is also a member of A9. So in general we say, if A and B are two sets such that for every x, x belonging to A implies x belonging to B. That means, look at this Venn diagram. We see every element of A belongs to is also an element of B. So we say that A is contained in B, or A is a subset of B, and this is the notation. Okay. Next is, yeah. So is there something? Okay. So we always see in notions that, okay, when we defined our empty set, we took one example as all the elements x such that x is not equal to x. So this is a trivial thing, right? Every element is equal to itself. So can you say that every set is a subset of itself? Well, yes. So there should be some concept which says if some set A is a subset of B, it could be either equal to it or smaller than it. So if you have to say something is smaller than that or a bigger set, then you define it as the proper subset. That is, this is the definition, the formal definition. If A is a subset of B but A is not equal to B. Yes, because this could imply that A and B both are equal to each other. Okay, that is, there exists at least one element in B such that it doesn't belong to A. It means A has to be smaller than B, right? Only then we can say that it is a proper subset of B. Yeah, so we saw that. We already know that every set is a subset of itself. So if I say if A is equal to B, I'll say A is a subset of B, and so remember this logical term, and B is also a subset of A. So these are equivalent statements. If I say every set is a subset of itself, then it means if they are equal, you can write it both ways. So if you have to prove two sets A and B are equal, you'll just be proving that A is a subset of B and B is also a subset of A. Okay, so now we see operations on set. What could be the operations? So set is some collection, right? So two different collections. What is the most obvious operation? Taking their union, combining them, addition. We say in terms of numbers. Here addition would be taking the union. So what is union now? If A and B are two sets, A union B is a set which contains all elements which belong to either of them. So look at this Venn diagram. All the elements in A as well as in B, right? So by definition you say A union B is the set of all x such that x belongs to A or B, the mathematical relation or. Okay.